All right, I'm gonna go ahead and get started here. What do you guys know about parallel lines? Anything? Parallel lines are pretty special in geometry. You have parallel lines, they can set up all kinds of different relationships. Go ahead and mute yourself, please. Thank you. Who else just got on here? Hey, Lily. All right. First thing first, of course, Odyssey Ware's got to give us some vocabulary. Parallel lines that are lines that have the same slope and never intersect. Railroad tracks, classic example of parallel lines. The sides of a window, those are parallel. The edges of a street or the sidewalk, those are parallel lines. Everything else, every other type of line is going to be an intersecting line. Because if they don't have the same slope, eventually they're going to intersect. Now, perpendicular lines are a special kind of intersecting line. You guys know the term perpendicular? Anybody know perpendicular? Perpendicular lines cross at right angles. They create 90-degree angles. And right here in the definition is a key phrase. They have opposite reciprocal slopes. And it sounds complicated, but it's really not. If you remember what a reciprocal is, I think we talked about this the other day, or maybe that was in algebra, I forget. Reciprocal.
I think it was in algebra.
Okay. Reciprocal is an essential term to know for pretty much any kind of math operation. The reciprocal is the flipped over version of any fraction or any whole number. The reciprocal of 1/4 is 4, or 4/1. Just flip it over. Now with perpendicular lines, it says opposite reciprocal. What that means is the sign is opposite. So if you have one that's negative, the other one's going to be positive. That's what it's referring to when talking about opposite reciprocal slopes. Of course, if we're talking about slope, we must be talking about something that's on a graph. So with perpendicular being a special kind of intersecting lines, there's also some things that we have to know about parallel lines. Right there at the top, things to remember when identifying parallel lines. Lines that have the same slope are parallel, so what do you have to find in order to determine if they're parallel? You're only going to look at the slope. If they have the same slope, then they're parallel. It's as simple as that. It's the rise over the run, all these different terms here. M, the change in y over the change in x, y2 minus y1 over x2 minus x1. All those are things that describe slope. Now, if you have an equation, sometimes that's even easier. If you have slope intercept, here it is in function notation. Here it is in traditional slope intercept, y equals mx plus b form. What are you going to look at there to determine the slope? What part of these equations represents the slope? Okay, do I need to call on somebody?
What was the question?
What part of these equations represents slope?
The rise over run.
Okay, I'm talking about these equations right here.
Would it be M?
It is M. That's right. So if you want to figure out just from an equation if lines are parallel, find the number that's in the position where M is. If the same number is there, the slope is the same, they are parallel. If the slope is opposite reciprocal, then they're perpendicular. So the key part of these slope-intercept equations for us, for parallel and perpendicular, is M. Now, if it's in standard form, then you're going to have to convert it by solving it for y. When you solve it for y, it goes from standard form into y equals mx plus b, and you'll be able to figure out where the slope is there. Very important thing here to keep in mind. Horizontal and vertical lines are always going to be perpendicular to each other. Now, the thing about a vertical line is the slope is undefined. So the opposite reciprocal is going to be 0. Those are those two special case lines, vertical and horizontal, special cases. So a lot of what we're going to be expected to do here at the beginning of this is to figure out whether lines are parallel or perpendicular. In this first example, we've got two equations. Neither one of them is in slope-intercept form. Well, they're not really in standard form either, but it doesn't matter because we can solve both of these equations for y and determine if the equations represent parallel or perpendicular lines. Solving for y is just an algebraic function. You know, we're going to cancel and manipulate, move terms around until we have the y by itself. And then you look and see what's in the position of M. And in this case, 2 is where M should be in both of those equations. So those two lines are parallel. So the next example gives you an equation in function notation. and it says find the slope of a line perpendicular to that line. Again, the only thing that's important is the slope. So you look at that equation, you see that m, the number where m normally is 2/3. So the opposite reciprocal is what they describe here. -3/2 for a perpendicular line. So these two rules here are going to be essential to remember. Parallel lines have the same slope. Perpendicular lines have the opposite reciprocal slope. But what if you're just given points? Well, the next example shows you how to go through that. You got to remember how to do those calculations. AB and CD are two different line segments, apparently. Are they parallel? Well, now you're going to have to calculate slopes. You could plot them on a graph. If you're very precise, you might be able to visually see that they are parallel. It's not guaranteed though. The calculations will guarantee that you've got it right. Because if the slope is the same, then they're parallel. I mean, if you got some graph paper and you're working with a ruler and you're very precise about how you draw it out on a graph, you probably could get the same result. Because once it's on the graph, then you could do rise and run on the graph and figure out that the slope is the same. They might visually look the same. They might look parallel, but it's still good to verify it numerically with the numbers.
So prove it.
Geometry is all about proof, man. Yep. Prove it, do the proof, so on. So let me get down here to one of these calculations. And I'm going to pause here on question number 6. We've got two sets of points. We've got a relationship between A, B, and C, D. And the answer choices is, are they neither parallel nor perpendicular, or are they parallel or perpendicular? So let's try some calculations here. So I think we've got a parallel set of lines here. So I'll go to the whiteboard. And I'll show the calculations that I did. For AB, I got -5 minus -2. Can't leave any signs out. 3 minus 1. So this is AB. For CD, I got 5 minus 2 over 5 minus 7. So here I got to keep change number with AB. Calculation on the top means these become positive. -5 plus 2 is -3. 3 minus 1 is 2. For CD, I got 5 minus 2, which is 3. And 5 minus 7 is -2. This is what I was referring to a minute ago when we were paused about having either one of the numbers be negative, then the whole thing is negative. Because this is not an opposite reciprocal here. These are just both two -3/2 slopes. So those are parallel. So y2 minus y1, x2 minus x1, and do that twice. They got questions on that? Okay, number 7 should be an easy one. What's the slope of the line that's parallel to that function?
-2.
Yeah, easy. Nothing to do but pick the number right out of the equation. That's right. What are you going to do with number 8 though?
You have to move 6x to the other side and then divide all sides by 3.
Excellent. You're going to convert it. That's, if you recognize that as an equation that's in standard form, it does not give you the slope. Standard form does not give you the slope. And was that Abby that just chimed in there?
Yeah, that
Great.
was me.
All right, great, thank you. Adding 6x helps us get the y started by its, we're starting to get it by itself. We do that on both sides. Divide every term by 3 then, so you got y equals -6x over 3 plus 12 over 3, so you would have a slope of 2. That's the answer that I would come up with. I don't even care about the y-intercept at that point. I just need to know the slope. So that's pretty much how those kind of problems are going to go until you get down here to number 9. What is the relationship of these lines? Y equals 5 and x equals 6. If you can't visualize it, scratch out a little graph. Are we parallel, perpendicular, or neither?
We would be perpendicular, right?
Good, I heard perpendicular from 2 different people. Excellent. And that's correct. So y equals 5. One, 2, 3, 4, 5. Y equals 5. Well, I just missed it, but I think you get the idea. There we go. Should be flat. That's better. Y equals 5 is here. X equals 6. Three, 4, 5, 6. X equals 6. It's going to be right through here. So those should cross at a 90-degree angle. Anytime you have a y equals line and an x equals line, they are going to cross at a 90-degree angle and be perpendicular. This is what I was talking about before with the vertical line having an undefined slope and the horizontal line having a slope of 0. So it can be kind of hard to understand what the negative reciprocal or opposite reciprocal is with these kind of lines. The nice thing is, these are things you can put on a graph and you can visualize them. Sketch it out. Don't try to do all this in your head. Put it on paper and look at it and see what you got. So any questions so far? Okay, properties of parallels. Parallel lines and planes. There are some basic properties. Lines in the same plane and have no points in common. Those are parallel lines. If you can imagine your desktop as a plane, if you drew two parallel lines on your desktop, the actual physical desk that you're sitting at, they would be in the same plane because they're on the desktop and they would have no points in common. Parallel planes are planes that have no points in common, like the ceiling and the floor in your room. Skew lines are lines that do not lie in the same plane. I could have a line on this wall over here to my left and a line going that way on the ceiling. They're not in the same plane. Those are going to be called skew. They don't intersect. They're not parallel or not perpendicular.
Lines or line segments are considered parallel if they are always the same distance apart and never intersect. Recall from algebra that parallel lines have the same slope. This would ensure that the lines are extending in the same direction and will not cross. Take a look at the diagram and think about parallel segments. If segments BE and FI were extended into lines, would they ever intersect? These two lines will never intersect, yet they do not have the same slopes, so they are not parallel. This leads you to a very important concept regarding the concept of parallelism that is new to the study of geometry. In order to be parallel, the objects must be in the same plane. A plane is an extended flat surface, like a sheet of paper that the objects could be drawn on.
The thing that makes these kind of examples a little tough to comprehend sometimes is they're trying to represent, again, three-dimensional shapes in 2 dimensions. So these dashed lines here, those are on the back side or the underneath side of this 5-sided shape. It looks like home plate, but it's 5 sides. If it were a solid, you would not be able to see this corner here or that edge or that edge. That's why they show them as dashed lines. So getting used to seeing these things in 2 dimensions when they're actually trying to represent a 3-dimensional shape can be a little challenging.
Lines BE and FI are called skew lines, as they are not parallel and will not intersect. Let's answer a few more questions about this diagram. Do you see 2 planes that are parallel? The top and bottom faces could be extended in all directions to form a plane, and they are parallel. Can you name 2 lines that are skew to line EF? In this figure, there are many lines that are skewed to line EJ. A couple of them are lines GI, CF, and AB. Can you name 3 sets of parallel segments? As there are 10 sets of parallel segments, identifying 3 of them is quick work. For example, segments AB and DE are parallel. Segments CF and GI are parallel. It is interesting to note that while segments CF and GI are parallel and CF is parallel to AD, they are not all parallel to each other as they do not exist in the same plane. Are segments CA and HB parallel or skew? Actually, they are neither, as they exist in the same plane, the top face, and they will eventually intersect.
It's one of those things that kind of hard to tell from the drawing. If you just looked at this casually, you might think that CA and BH are parallel. But that shape is kind of opening up. It's getting a little bit wider. The narrower part is down here on this side, AB, and it's getting wider as it goes towards C or towards H. So if you extended those on this direction, eventually they would cross.
So they're not skewed either.
Right, because Skew lines will never cross. They're not in the, and they're not parallel. You're always going to have a lot more skew lines in any shape than you will of any other type. Oops, I didn't mean to come out of that quite so quick. So when you get into more of these parallel situations, you start to look at shapes like a parallelogram. You have these sides here that are parallel and those sides parallel, the top and the bottom. A lot of different examples are going to be used here of parallel planes. They recreate or use the same one here as I mentioned before, the ceiling and the floor. Opposite walls can be parallel, front and back book covers. Those are parallel planes. If two parallel planes are cut by a third plane, then those lines of intersection are parallel. You're going to get into a lot of different rules here that may be hard to keep track of. So be sure as you're going through these theorems, you make some notes. Two parallel planes are cut by a third plane, then the lines of intersection are parallel. Well, that makes sense because A and B here are parallel. No matter which way you threw this third plane through there, this line here and this line they're calling L and the line they're calling M here on this other one, those are going to be parallel because they exist in planes that are already parallel. The other thing that you can get out of that is that anytime two planes intersect, you get a line. Parallel or not, two planes intersecting gives you a line. Two lines intersecting give you a point. Questions, anybody? So take some time to follow through on these proofs, read them in some detail, may have to go over them a couple times. And all these questions here in the lesson are going to be follow-up examples of to demonstrate those other, the original examples. Now, when you start getting into classifying angles, parallel lines, parallel planes can be a part of that. Not necessarily though, but they can be in some situations, and they can actually help you figure out what angle measures are. That's one of the more fun things to do with this stuff. Fun for me, probably not for you guys, but you know, I keep saying it, hoping that maybe one day it'll be true. Yeah, I know, I'm getting laughter on that one. So you got a bunch of angle descriptions here, defined terms. Acute angles, less than 90. Could be 89.9 degrees. It's still acute because it's less than 90. Adjacent, complementary, obtuse, right angle. There's only one measurement for right angles. It's always 90 degrees. Straight angle. If you've never heard that term before, it's referring to a line. A straight angle is an angle that measures exactly 180 degrees. Anybody know where that 180 comes from? Good, 90 and 90. And that is an excellent way to look at it. I got a circle. Circle is 360 degrees. I go straight across the circle at any point through the center. I'm cutting it into two semicircles, and that straight angle there, that straight line represents 180 degrees. If I add another, do what Nate said, 90 and 90, there's your 180. Doesn't necessarily have to be 90 and 90. Could be an acute angle and an obtuse angle. See, here's the acute angle. The rest of that would be the obtuse angle. Those are adjacent angles that total 180. Special kind of pair of angles. It's called a linear pair. Exactly right. Two angles together that total 180 degrees. So if you like drawing, this might be for you. Especially with all the circles and different angles and stuff like that that you can get into. Supplementary angles. A linear pair is always a set of supplementary angles because they always total 180. The vertex, I think you probably heard that term already. Vertex is where the two line segments, lines or rays meet to form an angle. Angles that are opposite from one another are vertical angles. Now this one is a little bit different than what you might think. I have two lines that cross. There's angle 1, angle 2, angle 3, angle 4. This is considered vertical angles. Now, none of those lines is vertical. This is where the definition, you're going to have to change your thinking a little bit, is this is not straight up and down lines. These are vertical here. 1 and 3 are vertical, considered a pair of vertical angles because they're congruent. 2 and 4 are congruent. Not vertical. These are still vertical angles. Vertical angles are congruent. Which is nice because if I told you that this angle is 70 degrees, so is this one. So what does that make? What does that make? I can't draw a half circle there. I'm trying to draw an arc from, what does that make angle number 2 if angle number 1 is 70?
110.
110, right. Because now you have adjacent angles that are that linear pair. Now you got another vertical angle across here that's number 4, also 110. So very soon here, what you get into are situations where you've got these configurations of different lines and they may only give you one angle measurement, but that's all you need to figure out all the rest. And they'll try to make it more complicated. You can bet on that. Sure it is. Okay, classifying angles really just means defining what type of angle it is. Right angles are always 90. Straight angle, 180. 38-degree angle is going to be acute. A 125-degree angle is going to be obtuse. Very straightforward. Now, Complementary and supplementary, though, are two ideas that people get confused on a lot. Complementary angles total 90 degrees. Supplementary total 180. Both of these examples here they're showing are adjacent angles. This angle and this angle. The other nice thing about complementary, a lot of times they're going to show the little 90-degree box there in the corner. That tells you that's a right angle. That tells you that automatically it's 90 degrees, so you know they're complementary. Here's what I was trying to draw on that other whiteboard, this arc here that shows you that half circle. That's another way to indicate that you've got 180 degrees. These, for supplementary, they can be separate or they can be adjacent. Here they're showing you two adjacent ones. But if you pulled those apart and had this angle and then drew the other one over here somewhere, they'd still be supplementary because they still, if you put them together, they're still going to equal 180. Here's my vertical angle drawing. And that's all it is. Really very, very uncomplicated.
So that would be vertical angle.
You got two sets of vertical angles in this example. Actually four, now that I see the way they've drawn it. This is one set here, 1, 2, 3, 4. All those angles around this intersection are vertical angles. 1 and 3 and 2 and 4 are going to be congruent. And you got another set of 4 more down here. 6 and 8 are going to be congruent. 5 and 7 are going to be congruent. Vertical angles are always going to come in pairs like that. And they're going to be the pairs that are congruent. Doesn't matter how many intersections you create, you're still going to create vertical angles. As long as it's just two lines intersecting, you still have that relationship of the opposite angles, the one opposing it, the one directly across from it being congruent. 1 and 4, 2 and 3, 6 and 7, 5 and 8, and so on. 9 and 12, 10 and 11. That's all they're showing you here, and that's reflected in the way they've identified those pairs. So from that, we get into measuring angles. And most of the time, it'll be fairly straightforward. It'll tell you the angles are complementary, so you have to remember that it's 90 degrees, like in this first example. So 90 minus 72 is going to give you what x equals. Two angles together equal 90. 72 plus x has to equal 90. You've got the right angle symbol in the corner there, so you know it's 90 total. So it's a simple calculation to figure out what x is. You just take 72 away from 90. And a lot of these calculations for angle measurements are going to be like that. Got to remember what's complementary and what's supplementary, though. If you mix it up, you won't get them right. Now this one here, the second example, those are supplementary. Right. Nathan said, so they have to equal 180, right. So they've written it out here as x plus 39 equals 180. You could just as easily say 180 minus 39 equals x. It's whatever makes the most sense to you. Questions, anybody? Now the next example is like what I did a minute ago on the whiteboard. If angle 1 is 82 degrees, I automatically know that angle 3 is also 82 degrees because of the definition of vertical angles. These two, 1 and 2 together, are supplementary because they create this straight angle. So 180 minus 82 is going to give me angle 2. Once I know what angle 2 is, I automatically know what angle 4 is because it's another pair of vertical angles. Now, with this shape here, with the 3 different lines crossing, they're going to give you one angle measurement in each corner of this drawing, but it doesn't change anything as far as how you figure out the rest. Here you got angle 2 in this group, got angle 8 over here in this group, angle 11 in this group, so it's exactly the same as if you just did one of those grouping individually. It's all the same process. Vertical angles and supplementary angles. So quite a few questions about that. Now we get back into angle definitions a little bit more after that section. The new terms here, this phrase, bisector of an angle. Now we've already had bisectors in terms of our lines. If we bisect a line or a line segment, we get the midpoint, which cuts a line into 2 equal parts. Bisector of an angle, the concept works exactly the same. We end up with 2 equal angles. Bisector cuts an angle in half. Part of what they're doing in this next example is helping you know how to describe these angles. And just like a lot of things in geometry, it's very specific. The letter where the vertex of the angle is always has to be in the middle of your description. For instance, this group right here, this angle, you can either call this angle 1 or you can call it angle ABC or CBA. If you start here, you can go the other direction. But in either case, either description, in either one of those descriptions, you notice that the vertex angle, the vertex letter is B, and it's in the middle. The vertex point or letter always has to be in the middle of your description. So you got options here. If there are letters there, you can use the letters. If you have a number, you can just call it by the number. The vertex always goes in the middle. If you've got multiple angles coming off of a single vertex, we can't just say, oh, this is angle A. Well, I don't know. I see 1, 2, 3 possible angles that all go to A. Which one is it? Well, now this is where you have to be very specific. Could be BAE, could be B, actually 4 angles. BAC, more than that even. CAE, CAD, DAE, etc. A lot of different angles can be described when you have points with their letters. They're showing you here some of the shapes of these angles. If you have an acute angle, right angles are always 90. Acute angles are skinny. They're less than 90. They're kind of closed. Obtuse angles are ones that are open up. They open up much wider than 90. Pretty obvious when you see these flatten out like this. they're getting closer and closer to being straight lines when you have an obtuse angle. It's greater than 90, not as much as 180. But they're much more wide open than an acute angle. Got an example here with this model about a bisector. You've got BD, this ray, bisecting this ABC. So now you've got two new angles that are equal. So you take that a step further, and it says if the measure, this little m here refers to the measure, if the measure of CBD, angle CBD is x plus 15, CBD, that's x plus 15. ABD, the measure of angle ABD over here is 2x minus 20.
You just solve for x.
Solve for x in what way? Yes, but how?
Well, x plus 15 equals 2x. That's where
Minus 20.
minus 20, and then you take the 20 to the 15, put it on the other side, so add 20. And you put the x over to the other side and add it to the 2x, and solve.
You got it.
Yeah.
Now what you're going to see there, and it's all based on the fact that this says you have a bisector. X plus 15 equals 2x minus 20. Those two angles were created to be equal because of the bisector. So now you can set them up as equal to each other since you have the descriptions of their measurements. Now you just got to solve for x. The funny thing is about that drawing is you might be tempted to make them equal to 90 because it almost looks like a 90-degree angle. Again, this is geometry. You cannot assume that. You can't say, oh, that's 90 degrees. It doesn't say that it's 90, and there's no square in the corner to show definitively that it's 90.
They're always going to be square.
If it's a right angle, it should always have a square in there or tell you that it's 90 degrees or that is a right angle. Because it's one of those special angles. That's why it's defined. So you're not going to have to guess. It'll be indicated one way or the other.
So this angle is most likely in acute or obtuse.
Probably acute. Probably two acute angles that make up one acute angle. So let's go back to the equation that I set up. Nate gave it to me. So solving for x now. If I take away x from both sides, I end up with 15 equals x minus 20. Now add 20 to both sides, I get 35 equals x. So plug it back in here. These both should equal 50. There's the first one, x plus 15. The second one, whoops, 2 times 35 minus 20. 2 times 35 is 70. Minus 20 is 50. Sure enough. Well, they're both 50. But look at that. When you add them together, they're 100. So it's actually the original angle is obtuse. But it sure doesn't look obtuse in the drawing. It looks very close to being 90. I guess the AV is kind of leaning out a little bit. So, but it's a good example of how you cannot assume any of these angle measurements without proof, without doing some calculations. And that's all because I used this definition of bisect. That told me that these two angles are going to be equal and allowed me to set up the equation and solve for x as a result. So you'll see a lot of that in these kind of problems. Questions, anybody? Now, when you get down to this part of this lesson, it says in your notebook, draw a right angle and then draw a bisector of the right angle, label all the parts. What are some properties of the angles formed by the bisector? You know, this is a good example of where you might not be able to put it in the answer box. You might just have to take a picture of it and send it to me. But what are you going to get when you bisect a right angle? Yeah, and how much are each one going to measure?
45.
You're going to get two 45-degree angles. That's right. They're both going to be acute. Anytime you bisect a 90, you're going to get half of that total, and they're going to be acute as a result because they're automatically going to be less than 90. Perpendicular angles, going to be dealing with that as a part of the definition also, because when you have perpendicular, you're creating 90-degree angles also. See if I can do that on my whiteboard here. I'm going to do this kind of backwards. Okay, that looks like a square. Right? It's not leaning over. It's not a parallelogram. So this line is going to be perpendicular to this line. Right? Has to be. It's also going to be perpendicular to this line down here. The squares have 90-degree angles, perpendicular, and if I took the square away, these lines would still be perpendicular. I don't know if I can draw it perpendicular quite as easily. See if I can put a square in there in the corner that makes it obvious. Well, pretty close. Perpendicular. Perpendicular lines always create those 90-degree angles, and that is something also that you'll use to help figure out angle measurements. And the last piece of this is specific to the angle measurements. We're not going to be using protractors, but we can certainly figure out angle measurements even without that.
The concept of angle is one of the most important concepts in geometry. The concepts of equality, sums, and differences of angles are important and will be used throughout this course. Measuring angles is pretty simple. The size of an angle is based on how wide the angle is open. To help you remember approximate sizes of angles, you will want to remember that a circle, once around, measures 360 degrees. If you removed a quarter of the circle, the angle created at the center of the circle would be 90 degrees. This you already know and is a right angle. If you cut one of the quarters in half, you would have half of 90 degrees, which is 45 degrees. It is beneficial to have a good mental picture of the approximate size of any angle. A protractor is the most common tool for measuring angles. For the purpose of this lesson, you will be given a protractor with different angle measurements and angles drawn on the protractor. Let's look at the following example. If angle TOK was 22 degrees, what is the measure of angle TOS?
Now, if this angle here is 22 degrees, you don't need a protractor to solve this. This is part of the reason why we don't have those. We're not going to worry about those, because all of these angles together, if I got a right angle here, I also have a right angle on this side. So all these together are going to total 180, but I don't even need that to be able to figure out what this yellow part of this angle is. All I got to do is take 90 minus 22. Because when I have this situation, this line here, this ray OS intersecting with KL at point O, and it's showing as a right angle, that means it's perpendicular. So both sides of that intersection are going to be perpendicular, creating two right angles. So I automatically know that this side over here is 90 degrees, the same as this side is 90 degrees. So 90 minus 22, 90 minus 20 is 70, it'd be 68 degrees for this other section. I don't need a protractor for that.
From the symbols in the illustration, you can see angle SOL is 90 degrees. Since this angle is supplementary with angle SOK, that means that angle SOK must also measure 90 degrees. Therefore, angle TOS is 90 minus 22, which is 68 degrees. If you know angle QOL is 49 degrees, what is the measure of angle TOQ? From the previous exercise, you determined that angle TOS was 68 degrees. By repeating the same process, you can determine that angle SOQ is 90 minus 49, which is equal to 41 degrees. Now, by the angle addition postulate, you can add angles TOS and SOQ to get angle TOQ. By substituting known...
He's doing this the hard way. I already know that this angle over here is 41, or excuse me, is 90 because of the square. I'm not going to go through all that. You can, but he's making it more difficult than it needs to be, because I'm going to add this 90 with this 68. If I want to know what TOQ is, then that's fine. We had to do this. If I need to know what this whole thing is, it's going to be 90 plus 68. The piece over here that we started with was 22. The point I'm trying to make here is that a lot of times in figuring out these angle measures, you're going to be using either 90 or 180, and you're figuring out what's missing in order to get back to a total of 90 or back to a total of 180. And you have to keep these answers in your notes, because it's probably going to come up again and get used as in another part of an extended problem.
Values for angles TOS and SOQ, you get the angle measure for angle TOQ is 109 degrees. What kind of angle is this? You're right. It is an obtuse angle. Being able to break large angles into smaller angles is a key strategy that you will often be able to use in solving problems.
Okay, any questions about any of that so far? Covered a lot of ground in those lessons today. There are actually 2 quizzes that covers this part of the lesson. I'll be available tomorrow for office hours. If you have questions, need any specific help on anything, be sure to text me. I have a couple of commitments in the afternoon tomorrow that will keep me away from the computer, but most of the day I'll be around. So if there's nothing else, I'll let you guys go and we'll either talk to you tomorrow or we'll see you on Thursday. All right?
Thank you, Jay.
All right. Thanks for being here, everybody.
Thank you. Bye.
Thanks for participating.